So I've got a really nice video today about something called the universal parabolic constant. But maybe before we talk about exactly what that is, let's recall that there are four classes of conic sections. There are circles and ellipses, and so sometimes circles and ellipses are put into the same class, but for our purposes, we'll think about them slightly differently. And then there are parabolas and hyperbolas. Now, it turns out that hyperbolas and ellipses are all slightly different from one another, and that difference is given by something called the eccentricity. However, parabolas are all similar to each other, and circles are all similar to each other. And so that similarity of all circles gives us something called the universal circle constant, but that has a much more common name known as pi. And so let's recall that pi is given as the ratio of the circumference of a circle to the diameter of a circle. Well, the fact that all parabolas are also similar to each other gives us the existence of something called the universal parabolic constant. So to talk about that a little bit more deeply, let's get a picture of a parabola on the board. So now we've got our parabola on the board, as well as the things that define that parabola. Let's recall that a parabola is really defined to be the set of points that are equidistant from a fixed line known as the directrix and a fixed point known as the focus. And along with that, kind of for free, we get something called the axis of symmetry. So just to reiterate what's going on here, if we go over here to this point, maybe up here, and then we measure down to the line, well, we have to measure to the line along a right angle, and then we measure over here to the point, we get the same length. So those two line segments have the same length. Okay, so that's just a little bit of a reminder of how a parabola is carefully defined. Now let's talk about what the universal parabolic constant is. Well, we need to put a horizontal line going through the focus that's going to cut the parabola. So that'll cut the parabola right here, as well as it'll cut the parabola right here. And this line has a name, or this line segment, I should say, has a name, and that's called the latus rectum. And then once we have that in place, we can define this parabolic constant. And this parabolic constant is the length of this blue arc. So that's a certain arc of the parabola. Maybe I'll say that that has length L1. And then divided by the length of this brown line segment, which is the distance from the directrix up to the focus. I'll call that L2. So like I said, this universal parabolic constant will be equal to, well, I'll call it P. And it is this L1 divided by L2. Well, it's not super clear that this ratio is always fixed, but that's exactly what we'll show for the rest of this video, as well as calculate this in terms of some more well-known constants. Okay, so now let's get to it. So I'll set this up so my axis of symmetry is the y-axis. And then I'll say my focus lies at the point 0, f. Okay, so that's good. Then I'll also put the origin down here. So that means this will be my x-axis, but that gives me an equation for my directrix. My directrix will have equation y equals minus f. But that immediately tells me that this length L2 is equal to 2f, the distance from the directrix up to the focus. Now, next up, what we'd like to do is find an equation for this parabola. And we can do that by setting this guy right here equal to the coordinate xy. and then measuring this distance two different ways. So we'll measure the distance this way first. So that's not too hard because since this is a right angle, we know this coordinate down here will be x comma minus f. And then given that we have this coordinate right here, 0f, we can use maybe just the distance formula to calculate that. Okay, so let's calculate this distance first. So let's see, that's going to be y minus negative f or y plus f. So we have y plus f is equal to the square root of the distance in the x parts, which is just x squared, and the distance in the y part, so that's going to be plus y minus f squared. So we're left with something like that. Now we can square that and solve for y, so let's do that. So squaring this side gives us y squared plus 2yf plus f squared. And then squaring this side will get rid of the square root, so that'll give me x squared. And then I'll distribute this out as well, so that'll be y squared minus 2yf plus f squared. And now some stuff cancels. So notice this y squared cancels this y squared. And then likewise, this f squared cancels this f squared. But that's actually pretty nice because now we have these two terms that involve y, and then this single term right here that involves x, allowing us to solve y equals 1 over 4f times x squared. So that's kind of a pretty nice formula for this parabola. So let's maybe write that in here. So we've got this as y equals, I'll call it x squared over 4f. Okay, nice. Now that we've got that taken care of, we're ready to make this calculation. Okay, now we're ready to make this calculation. So we'll have P is equal to L1. So L1 is this arc length of our parabola between, well, by a quick calculation, we can see this right here is minus 2f, and this part right here is 2f. So it's the arc length between x equals negative 2f and x equals 2f of our parabola. But there's a nice equation for arc length, and that's given by an integral. We have the integral from minus 2f to 2f of the square root of 1 plus the derivative of the equation of this parabola squared. So let's quickly notice that if we take the derivative of y, we'll get 2x over 2f, so that'll be x over 2f. Or I should say 2x over 4f, but then some 2's cancel. Then we need to square that, so that gives us x squared over 4f squared. So then we'll have this is dx. Then we need to divide by L2, but we already know that L2 is 2f. So we've got this as 1 over 2f. Okay, nice. And now we'll do a change of variables. So let's maybe set u equal to maybe x over 2f. That means u squared is x squared over, let's see, 4f squared. So that's pretty useful for what we have right here because we see this term is equal to u squared. Okay. But now that tells us that du is equal to dx over 2f, which means we can replace this 1 over 2f dx with du based off of that. Okay, nice. So that's going to end up leaving us with the integral of 1 plus u squared du. Now we have to think about the bounds of integration. So when x is negative 2f, u is negative 1. And then likewise, when x is 2f, u is equal to 1. So we've got our parabolic constant is just that. And I think we can already see that this will be a constant because there's no f's left in here. Recall f was equal to the focus. F was like the one kind of unique thing attached to this parabola. So that's been like sorted out with this change of variables. Okay, so now we need to finish it off by making this calculation. First, let's notice that this is an even function, so we can make this 2 times the integral from 0 to 1 of 1 plus u squared du. And then this really screams for us to take a trigonometric substitution. And so the standard trig substitution here would be u equals tangent theta. That means du is equal to secant squared theta d theta, like that. But now let's see what that's going to give us. That's going to give us 2, and then the integral from 0 to pi over 4. Where did that pi over 4 come from? Well, notice when tangent theta is equal to 1, theta is equal to pi over 4, and then we'll have secant cubed theta d theta. So one of those secant thetas comes from 1 plus u squared, just using trigonometric identities, and the other one comes from du. So now we're right there. Okay, so now let's maybe bring that up and then we'll finish it off. So here's where we left our calculation. Our parabolic constant was equal to 2 times the integral from 0 to pi over 4 of secant cubed theta d theta. Now we're going to finish this off with a combination of integration by parts and one of my favorite tricks. So the trick that I'll use here is to erase this 2 and then add another copy of this integral in. But the other copy I'll write as the integral from 0 to pi over 4 of secant theta times secant squared theta d theta. So I haven't changed anything here. And now I'll take that second copy and I'll calculate it using integration by parts. So this will be my dv term, and this will be my u term. You might say, well, how do I know that that's a good choice for u and dv? And the answer is that I know how to take the antiderivative of secant squared pretty easily. So for instance, we know that v here will be equal to tangent theta because the derivative of tangent is secant squared. Furthermore, we know du will be tangent theta times secant theta d theta, again, just from the standard derivative rule for the secant. Now we'll use our integration by parts formula. Let's recall that that says that the integral of u dv is equal to u times v minus the integral of v du. So we can rewrite this whole thing without changing our first integral, so 0 to pi over 4 secant cubed theta d theta, plus, like I said, u times v, so that'll be secant theta tangent theta evaluated from 0 to pi over 4, and then minus the integral from 0 to pi over 4 of v du. So let's see, that's going to be tangent squared theta secant theta d theta. So we're left with something like that. Now let's see where we're at. So if we take secant of pi over 4, that's going to give us the square root of 2. So let's maybe circle that in orange. So secant of pi over 4, like I said, is square root of 2. It's because it's 1 over cosine. Tangent of pi over 4 is 1. And then secant of 0 is 1, whereas tangent of 0 is 0. So that's the simplification that we get here. Furthermore, we can use one of our trig identities to take this tangent theta and write it as secant squared theta minus 1. So let's see where that leaves us. So we've got this whole thing is equal to the integral from 0 to pi over 4 of secant cubed theta d theta plus the square root of 2. That's what we get from this. And then minus the integral from 0 to pi over 4 of secant cubed theta d theta. That comes from this secant squared times this secant, and then plus the integral from 0 to pi over 4 of secant theta d theta. That comes from this minus sign, this minus 1, and then that secant theta. Now here's where the magic starts to happen. So notice this secant cubed and this secant cubed will cancel. They're attached to opposite signs. And then we can use the standard antiderivative for secant. So let's recall that that is the natural log of the absolute value of secant theta plus tangent theta. We need to evaluate that from 0 to pi over 4. So just as we did before, evaluating this at pi over 4 will give us square root of 2 plus 1. Evaluating this at 0 will give us the number 1. Natural log of the number 1 is 0, leaving us in the end with the square root of 2 plus natural log of, I'll write it as 1 plus the square root of 2. And that would be our final kind of nice expression for this parabolic constant. And that's a good place to stop.